So now we'll get into some of the challenges that we've been dealing with. So this is just kind of a side profile of a LiDAR data set or a DEM data set. So you can imagine that this would be, a 1 meter pixel. We're just kind of looking at it from the side here. So the wet areas mapping as it currently exists is entirely based on overland flow. So it's a topographic soil moisture model. So when we start to look at our flow direction that I showed previously, flow would want to come down this hill, but there's going to be a sink or a depression right here. So these can sometimes be artifacts associated with the classification of the bare earth on the LiDAR data. Sometimes it's an actual feature that exists. But from an overland flow perspective, these things have to be resolved one way or another in order to have our flow continuity to continue properly throughout the entire data set. So there's two different ways to do that. There's one called filling. And essentially with that, we're going to flood the landscape until none of these features exist. So what we can see here is this would be the impact to this data if we were to fill to remove these depressions. The other way is called breaching. And through breaching, we lower the elevation of any of these impoundments in order to have flow continue across. There's pros and cons to each of these, but the majority of processing that's been done currently, and what used to be done in our earlier phases, was all based on filling, because that's kind of the least computationally intensive, and it's the most readily available. As an example, through ArcGIS, filling is available, but breaching is not. So that's just something to consider. So that was kind of how we started with our earlier phases on this project, and as we move forward, we started to advance some of this data, some of the methodologies that we used. So what we started to look at was LiDAR data was kind of noisy when we started to look at all these kind of micro sinks and the micro topography that exists based on the classification of the bare earth LiDAR. So we started to look at something called pre-filling. So that's the removal of any sink that can be completely resolved by filling to a very, very small number. So what we'll show here, this is again a couple of different areas in theory, and we'll just show some 5 centimeter gradations. So from a pre-filling methodology, we can say that this small sink could be entirely resolved, by filling a matter of say 2 centimeters, right? In this other area, we could see that in order to resolve that sink, we would have to fill 18 to 20 centimeters, right? So from our methods of pre-filling, we can say, okay, we will allow the area on the left to be pre-filled, and we will maintain that sink on the right to be processed through a different method. So the impact of pre-filling can be fairly substantial. By just modifying our pre-fill depths, if we just fill every sink at 5 centimeter depth, we can actually remove about 60% of all the sinks across the landscape. By filling up to about 15 centimeters, we can remove up to 80%. And we're considering millions and millions of sinks when we're talking about 25 million hectares of processing area, right? With very, very minimal impact on the actual vertical data in the majority of the tiles. So with the vertical accuracy of the GOA LiDAR, it's plus or minus 30 centimeters, right? When we pre-fill to 15 centimeters, we're still substantially below the vertical accuracy thresholds, but we can remove a very substantial number of sinks and subsequently reduce the processing effort required to resolve the remaining sinks. So this is just an example LiDAR area. So what often happens with the LiDAR is through the requirements of the specs of the LiDAR to the vendor, oftentimes bridges are removed from the data. So what we're seeing down south here, it might be difficult to see, but this is actually a bridge that crosses this channel. So the bridge has been removed from the LiDAR. So flow is expected that it's probably going to continue fairly unobstructed through this area. But the area on the north here, there's a culvert in this area, and there's generally no requirement from a vendor to hydrologically condition or remove the road at this area. So as we'd shown before, the LiDAR sensors in the belly of an aircraft shoot their pulses down. They're not X-ray. They don't know that there's a culvert there. All they see is the top of the road. So this area has to be dealt with, otherwise we're going to have some issues, right? So in this area, we had 39,000 sinks in this relatively small area. This is the number of sinks that remain after 15 centimeter pre-filling. So we take it down, we remove about 71% in this particular instance of the sinks. We remove about 30,000 sinks from additional processing just by doing that pre-filling of 15 centimeters. But we can see that there's still some substantial sized sinks here. We can see that there's a large impoundment on the upstream side of this road because of that culvert that exists that isn't currently enforced into the LiDAR data. And if we were to imagine a beaver out in that area and they were to plug that culvert, this is what we could potentially expect to see from a flooding perspective. So there is some value in terms of having this sink data. What we can also see is there's a lot of depressions and sinks that still remain within the meanders of this channel. Oftentimes there's issues when there's some grassy vegetation and different things like that, that the LiDAR can't actually penetrate that fairly dense vegetation to get an actual true representation of the bare ground. And there's also some problems with the interaction with the LiDAR laser energy with water features.
This is image based on a raster or TIN, because it looks like a TIN.
This is raster. There's just interpolation across large areas up here. It's the rasterization of this data set was, we took the points, converted to tin, then to raster. So that was how this was done. There's just some tinned areas through the large areas where there was no LiDAR points. So, but this is all raster-based methodologies. Okay. So this is what we see, for the remaining sinks after the prefill methods. So after that, we started to look at a couple different breaching methods. So the first I called anthropogenic breaching, which is basically when we're going to breach any man-made features, right? Because those should be dealt with differently than natural features, because their forms are different than natural features. So we had to come up with a certain breach logic for how we would deal with these anthropogenic features. So our logic for this was we would have a shorter distance of breach with a more aggressive cutting of elevation values. Because if you imagine the culvert that exists across that road, we want it to cross from the upside to the bottom side of that road, regardless of the height of the road, right? We don't want it to be a very natural system that would try to go down the side of the ditch and eventually cross at a low point in the road. Because in actual fact, these are culverts that exist that cross, directly across the road. So I'll show you as we move forward what I mean by this, and hopefully it will become a bit more clear. Now, in order to do this, we needed to have our anthropogenic footprint. We needed to know where these features existed. So I had to come up with some road extraction algorithms based off of the bare earth LiDAR DEM to tell us where the roads were. We have some mapped road layers, but they're not always necessarily going to be fully complete or totally congruent with the high precision LiDAR data. So I came up with some methods that identified these road features based on topographic position, surface roughness, and linearity of different features extracted from the LiDAR data. So there's a bit of topographic analysis and a bit of computer visioning methodology that were implemented for this road extraction algorithm. So again, we're back to the same area that we showed previously. So now in red, we're seeing the predicted road extraction. So it does a fairly good job at picking out the extent of these road features. So when we know where the roads exist, and we saw where those impoundments existed, now we can start to identify the impoundments that we will choose to process based off of this anthropogenic breaching methodology. So if we remember, there was that large impoundment on the upside of this road, and through the anthropogenic breaching, which again is fairly aggressive because the height of the road had to be lowered substantially within those few raster cells in order to breach across that road. So when we do that, this is the remaining sinks. So obviously we've resolved entirely that sink on the north side of the road, but we still have all these other features. Now, if we were to try to implement this aggressive anthropogenic breaching within these meandering streams, we might have issues where we try to resolve a sink in this area by cutting across here, because this would be a more aggressive breach. But in actual fact, we know that the meander is a slow turn around this area. So we had to deal with these in a slightly different way. So next we implemented a natural breaching method. So this is, as the name implies, how we try to resolve the breaches in any of these naturally occurring features across the landscape, like these slowly meandering oxbows and different features like that. So the breach logic for this is a longer distance of breach with a less aggressive elevation change. So the way that we dealt with that is through we adopted some methodologies from a Saga GIS software suite. It's very computationally effective, or intensive, I guess, because there's a lot of different cost matrices associated with determining the proper direction that you're going to flow. Because again, we're dealing with longer distances, so there's a lot of different probability analysis that has to go into defining the proper locations of these breaches. It's very intensive, but it's worth it. It's worth the effort. So as you can see in this area, these red lines are the results of the natural breaching to resolve the sinks within this data set. So we can see that we didn't really have to change the values of a lot of cells to completely resolve all those sinks out. But by lowering them down, whatever it may have been, 20 centimeters, within the depth of that actual channel location, we can maintain a lot of the topography that exists within that channel network, which again is going to improve the resulting stream channels and the subsequent wet areas rasters. So once all of that hydro conditioning is done and all the proper breaching is enforced, we have our properly unimpeded overland flow. So we've maintained the majority of the topographic information inherent in the LiDAR data and still allowed for proper hydrological integrity of the data to have our continuous flow across the landscape. So this is some of the work that's been done over the past year, actually more or less 6 months, to try to improve the data sets that we currently have, both for EMEND and as we move forward across the province. And again, the wood areas rasters that exist based off of this improved hydrologically conditioned DEM data set. So this is what the product would have looked like in the previous phases, so our earlier methods, when we just implement a full fill. So you can see, obviously we're losing a lot of topographic information that's very valuable and important within this LiDAR data. When we fill, we have no idea what's actually happening in this area. It might be difficult to see from the back there, but we can also see that all these areas are now flooded. So we're going to end up with some straight line segments that exist across here because, again, we've lost all the topography within these zones. And this is the optimally conditioned, as we call it, hydro-conditioned DEM for the same area. So this is with the pre-filling of 5 centimeters in this case, and the 2 different breaching methodologies that we talked about. So again, we're looking at a perfectly conditioned DEM where there's no more sinks that exist, but we've maintained the majority of the topography within this data set. So again, just a bit of a side-by-side comparison of the before and after methods that we used to deal with and that we currently have now. So a bit of a summary. So we talked about pre-filling and how it reduces the processing time required to resolve those remaining sinks. And especially when we're talking about the computationally intensive natural breaching, the fewer sinks we have to process, the better. The anthropogenic breaching resolves a lot of the damming at roadside, but it requires knowledge of the locations of these road features. So the road extraction methods had to be developed. And again, the natural breaching resolves the remaining sinks. It's very intensive, but it's again worth the wait. So just a bit of a summary here. So if we have a look at the change in elevation required for each of those methods versus the number of cells altered, the anthropogenic breaching changes fewer cells with the higher elevation change. Natural breaching is more cells with the lower elevation change. And the standard depression filling is kind of the worst of both worlds, where there's more cells with a higher elevation change that actually have to be, affected within the LiDAR data. So back to this EMEND area here. So we're looking at the bridge in EMEND, just a few kilometers north of the gazebo. So right now we're looking at the base flow stream representation. So this is the streamline network that currently exists within the GOA. So we can see it does a fairly good job. It's a little bit crude through some of those meanders, but from a broad brush approach, I think it's fairly good. When we look at the filled-based stream channel delineation, we can see a lot of straight lines now on that upper side. That's because, again, we lost all the topographic information within this zone, so it essentially just flowed across the top of these filled surfaces. So in the previous versions of the wood areas rasters that we delivered, and also I believe in the previous versions for EMEND, this was an issue in some of the areas. In the subsequent versions that we've finished processing just last week, we've gone to this hydrologically conditioned, properly conditioned DEM data set. So now we're going to have a lot better integrity of the proper flows throughout these meanders and things like that. So again, it might be a little difficult to see, but this is just all 3 of the different data layers we were just talking about. We can kind of see the pros and cons of each, but it's fairly apparent to me that the hydro conditioned in blue seems to be the most accurate, most precise, both through here as we're not cutting through uplands, as well as maintaining the proper meanders throughout the stream network.